Hello everyone, welcome to my programming club. Today we will be solving another daily Leetcode problem, and the problem's name is out of boundary paths. So the problem statement goes like this. There is a M cross N grid with a ball. The ball initially is at the position start row and start column. You are allowed to move the ball on the 4 adjacent cells in the grid. Okay, possibly out of the grid also. You can apply at most max moves. Okay, so in each move you can move a ball to one of its adjacent 4 sides. What are those adjacent 4 sides? Let's say ball is initially situated in a cell. Let's say this was the playground. It is divided into cells, and your ball was initially here. So you can move your ball in one move in either of these cells. Okay, these are the 4 adjacent cells that you can move into. So this can move here, 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 or here. So I hope you are able to understand. Now coming back towards the problem, given the 5 integers mn, which will stands for number of rows and number of columns respectively, max move, the number of moves you can make, start row and start column will be the initial coordinates of the row of the cell in which the ball is currently in. Return the number of paths to move the ball out of the grid boundary. Okay, so you have to somehow move this ball outside the grid boundary, and you have to return what will be the total number of paths that will be possible. Okay, to move the ball out of the boundary of the grid by using at most max moves, max moves, number of moves. Okay, since the answer can be very large, we are told to use the modulo. So modular arithmetic should be used while adding the contributions of each path. Now let's have a look at the constraints. The number of rows and columns will be of order 50. Moves will also be of order 50. Start row and start column will be lying well within the boundaries of the grid, or say playground, whatever you may prefer. So let's see how we'll be solving this particular problem. Okay, so first of all we will be considering a brute force approach. Try out all possible paths. uh, while staying within the bounds of or say limits of max moves. Okay, these number of moves are allowed only. So let's say there were n moves allowed. This is move 1, and similarly it will go until move n. Now for each of these moves you will be having 4 options. 4, 4, 4, 4, 4, 4. Why I am calling 4 options? Because there are 4 possible directions. We are not bothered about whether it will end us up in boundaries of the playground or not, but if we consider a loose limit, then you can say that these number of total options or total paths can be possible if you are considering only using max number of moves, at most max number of moves. So which is nothing but order of 4 raised to power max moves. Okay, and what are the max what is the max moves order? It is 50, so it will be nothing but 2 raised to power 100. Okay, because 4 is 2 raised to power 2, and if you have a power of 50, then these two will multiply and 2 raised to power 100 will be there. So this will be the order of number of operations that your program will be requiring to solve this particular problem. Number of operations required by brute force solution. And if there is a concept that these number of operations, if it is greater than order of 10 raised to power 8 operations, so this is our operation limit. If the number of operations required by your program to solve a particular program reaches this limit or exceeds this limit, then you may get a TLE and your solution will not be accepted. Okay, so your solution will be not accepted. So TLE will be there, and in order to get this solution accepted, we have to do some optimizations here. Okay, so for that we will be making two observations. First observation being, let's say there was a path which was having transitions like this A, B, C, D. Let's say these were 4 move path, so max move value was 4, and these were the cells that you moved into. Okay, and let's say there was this is let's say path 1. There was another path that you followed, and it was having very much similar trajectory, other than that instead of D it was E. Okay, so if you observe, this part is same in both of the columns. Okay, so both of the paths, you can say, is having same subpart or subproblem. So calculations for this particular part will be done more than once, and it will lead to extra work. Okay, so the first property is satisfied by this problem, which is overlapping subproblems. Okay, now let's talk about another property. Now let's say you were required to find what will be the number of paths leading to D. Okay, so since you know that we can end up on D by 4 directions. Let's say you can arrive at D via 4 directions. Okay, so we need to know what were the results for these 4 directions. So it can be said that solution of bigger subproblem can be derived from combining the solutions of smaller subproblems. Because let's say at move number m you let's say move num m num, you were at D, then you will see where were you at m num minus 1th move. Okay, so at this particular move, this was the previous move, you could have been at these four adjacent places to D. So these were indeed smaller subproblems, bigger subproblem being uh, the current location at move number this. Okay, so this was another observation that solution of bigger subproblems can be derived by combining solutions of smaller subproblems. So the second observation's name is optimal substructure. Those of you who are new to these two properties of a particular problem, I will be providing a link describing these two properties. Okay, so if a problem satisfies these two properties, then optimization technique can be applied here, which is called dynamic programming. I will also be providing a link for an article describing what dynamic programming is. Right now what I can tell you is, you store the solutions of each of the state that is occurring till you reach your final answer. Okay, and if let's say this state occurs again, let's say you stored it somewhere, stored the result for this somewhere. Okay, then instead of recalculating it, you just refer to your result. Okay, and you will be able to avoid extra work. So it is a twofold process: avoiding extra work and building a solution of bigger subproblems based upon solution of smaller subproblems. Okay, so let's see how we can apply dynamic programming here. Let me quickly take a new slide. Let's say you are at this index. Then in these type of questions, you should be asking yourself, let's say, first of all, what will be the variables that will define your current state? Okay, so what variables define current state? So at a particular move number, let's say there were n moves, you would be at a certain position. Okay, so that certain position can be represented by a grid. So each of these n moves will have one grid of itself. Okay, grid or say playground, whichever you may prefer to call it. It entirely depends upon you, but in each of these moves, you can say the state of the playground will change. Okay, so let's say initially you are here on the first move, then you make your first move. This was the 0th initial position. Then you made your first move, and the second grid that will be looking, now the grid will look something like this. Okay, so you moved from here to, let's say, here. So now grid is looking something like this. So this is a new state of grid. So it was just one move back. So each of the move will have some state of grid. Okay, a different state of grid or same state also. Not same state, you cannot stay in a particular position in two consecutive moves. Okay, so each move will have a board of its own. Okay, board state of its own. Then for each of these states, let's say you are on this state, so how could you have ended on this state? You could have been placed at this state by moving from these four possible directions. Okay, so let's say you were at this state and then you decided to move at this one, and it is possible that you were here, then you move to here, and it is also possible, let's say there is more number of rows. Let's say you were here, then you decided to move here. Okay, another possibility that is there is, let's say you were here and you decided to move here. So four possibilities are there. So in total, what are the variables that are defining your current state? So it is move number, certainly, and the coordinates which are presently of your ball. Okay, which represent your ball on the this board or field, whatever you may want to call it. So row and column, these are the three states that state variables that define the current state variables. So now we came to know that we will be requiring three state variables to define a current state. Okay, so we will be using a 3D dynamic programming structure. The number of dimensions of the dynamic programming structure that we will be using to store results will dependent upon the number of state variables that there are. Okay, since there were three, so we will be using a 3D structure to store the intermediate results. So let's say you are on, let's say we define that dynamic programming structure as path count. Okay, so on a particular move number, you were at R comma C or R colon C cell. Okay, then how many paths could have led to this particular cell? How many paths lead to this state, or how many paths or say states, previous states? This is your current state. So it will be nothing but you will consider yourself one move backward, which will be move number -1. Now whatever was the state of board on this particular move, that will be the previous, those will be the previous states to your current state. What I am talking about is, let's say at move num you are here. Okay, you are in this block. So how many directions are possible in move num -1 that could have led you here? These are nothing but this direction, this direction, this one, and this one. Okay, four possible directions are there in the previous move. So you will be taking all the contributions of these previous four states, which are nothing but, what is this? Let's call this R colon C. Okay, then this is path count of move num -1, since we are considering one move backwards, and this is nothing but, if you consider this one as R colon C, then if this is the rth row and one column before it will be R C -1. Similarly, you will keep all the previous states and use their contribution. So what all previous states will be? Let me write clearly on the next slide. So move num -1 will also be there, since you are having one move backwards. Okay, so other states can be one row above or let's say one row below. Okay, and another state can be one column before, or let's say one column after the current column. Okay, and this move number -1 will also always be there. Okay, so you will be adding contributions of all these states, path count here also, and contributions of all these states will be added to path count, current move number, and current location of the ball in this particular move number. Okay, so these contributions will be added to your current state. So this is your current state. And these are your previous states possible. Right now we are not worried about whether it will be within boundaries or not. We'll take care of that in the implementation part, but seems like we are having a transition equation. So this is our transition equation. Transition from what to what? Current state, previous state to current state. Okay, so let's see the implementation part. So this is the implementation part. This was for debugging only. I am removing it as of now. So for each move number, there will be a different board state. First of all, if let's say there are 0 moves allowed, it is mentioned that move number can be 0 also, nummax moves. So you will return 0. Other than that, this structure will be allowed to use to store the results of each subproblem and use the results of smaller subproblems to build the results of bigger subproblem. Okay, and these will be the 4 directions that will be possible. From current cell. Okay, and for each board, for each move number, we are considering different board. Board or say playground state, whichever you may want to call it, it totally depends upon you. Okay, so for each of the move number there will be a different grid. Okay, so this is previous state contribution. What previous states will contribute to your current state? Okay, so we have discussed that there can be 4 possible previous states. Okay, and if let's say your previous states are lying outside the boundaries of your board, okay, it is not within the boundaries, then you will simply add 1, since if the goal is to move the ball outside the boundary, it is mentioned here. Okay, to move the ball out of the grid boundary. So since goal was to move ball outside the boundary, if the previous state is outside grid boundary, then we will add 1 as previous state 1 to previous state contribution. Okay, and this will be your current state. You will be adding 1 to your current state, not current 1, previous state contribution to your current state. Okay, and at last you will return the number of paths leading to initial start row and start column, initial position, number of out of grid boundary paths leading to initial position of ball. Okay, so if you are worried about these are nothing but just boundary checks. If let's say you are on the very first move, then there is no previous move. In that case, previous moves will contribute nothing to towards your move if it is within the boundary, and if your previous state is not within the boundary, then it will be contributing 1. Okay, so that is this thing, and this is just a function to check whether you are within the boundaries of the grid or not. Okay, and this is how we will be solving this particular problem. And if you are still having any queries or any doubts, then please feel free to use the comment section. Thank you for watching.